Okay, time to get started. So, new kind of integral we're going to talk about today. We've done a lot of different kinds of integrals so far in the course. Actually, come to think of it, we're going to do 3, maybe 4 new kinds of integrals today. So lots going to happen. Let's see how much time permits. So, the new twist, the variation that's going to happen today is that we're going to start considering integrals where the integrand is no longer a scalar. So you remember last time we spent a lot of time talking about vector fields. There's this new kind of an object where at a point, instead of associating a number like density or population density or concentrations, anything along those lines, instead of a scalar quantity, so we associate a vector, right? And so the gravitational field, let's say, of a planet or an electric field given charged particles, at every point, it's not that there's some scalar number, it's at every point there is a vector indicating both a magnitude and a direction. And it's going to turn out that it makes pretty good sense, and there's some nice applications if you consider the question of what would it mean to take an integral of such a thing. So our first example of that will be something called a vector line integral. Rather than write the formula down, let me start with a motivation. And we've done this with a lot of different kind of integrals. Take double integrals, for example. We started off with a geometry question. How much volume is there under the graph of a certain function? So here's the question we're going to consider for this next kind of integral. We're going to compute work. So this is a physics application instead of a geometry application, but still, it's a perfectly natural application. So I could ask, suppose I were moving along a curve, and as I move along the curve, I'm having to apply some force. Maybe the force that I'm having to apply is to overcome a force that's being applied on me. So, for example, maybe there's wind blowing as I walk along this path, and the wind's blowing really hard, and I have to kind of push, into the path that I'm walking, just to keep from falling over, just to overcome the force that's being applied to me. So, question: how much work does it take to walk along this path? Well, now you might recall from long ago, this is very early in the course. We wrote down this formula: work equals force dot displacement. And this was from chapter 1. It's a variation on an old high school formula. Work equals force times distance. Right? That old high school formula didn't account for angles and components and stuff. So this is the more sophisticated version, keeping in mind that force is not a scalar, force is a vector. Displacement's not just a scalar distance, it's also a direction. And the dot product here keeps track of how those directions relate to each other. So this is sort of the more sophisticated replacement work equals force dot displacement. This formula, though, still makes certain assumptions that are not always true. This assumes that the force is constant over the entire process. Well, here, the force that's being applied on me looks like about like that. Whereas at this point over here, looks like the force that's being applied to me is about like that. That's a different vector. So I can't, in this situation, just say, oh yeah, just take the force and dot it with the displacement. Furthermore, I'm not going in a straight line from A to B. I'm going along a curve. That old chapter 1 formula doesn't account for that. So we need to find a variation of that old chapter 1 formula to account for this really more physically natural situation. If you think about it, forces in general just not constant. Gravitational fields, not constant, unless you're near the surface of the Earth. And paths that people follow, not always straight lines. Right? So, reasonable questions. So here's the idea. The idea is that we're going to acknowledge that work is something that accumulates along this curve. I guess I'll zoom out one notch. So work, the grand total amount of work that it takes to start there and end there is the sum of the amounts of work that it takes to move along each little piece of that path. So again, it's an accumulating quantity. So I can break this problem up into small pieces, look at one little piece at a time, talk, for example, on that little piece. of the curve. How much work does it take to move across that one little piece of curve? And then once I understand that, I can add that up over all the pieces. So in particular then, here's the nearby that one piece. Here's the forces that's being applied to me, thus requiring me to apply the negative of that force. Right? The green represents the wind blowing in my face, so the blue represents me pushing back against the wind. It's the sort of opposite forces. And I'm going to be applying that force as I move along this little piece of curve, which for a sufficiently small piece of curve is approximately straight. I'm approximately moving in a straight line displacement. Okay. So on the little piece of curve, whoops, this reduces to an old formula. We already have it again back in chapter 1. If you have a roughly constant, well, we're going to say constant force applied over a straight line displacement, then force dot displacement computes that amount of work. So that's what we put. Get the zoom back in. So in looking at how work accumulates on each little piece, the amount of work is force dot displacement. All right, so that's what we're going to be accumulating over all the little pieces, and so grand total, the amount of work it takes to move along that path is computed by that expression. Now let's talk about this expression. Now what is this? Looks kind of, sort of like an integral. Not exactly. Kind of different. For one thing, there's vectors all over the place. That's new. Right? There's a vector field here, F. This is not length, ds, delta s. This is a displacement vector. Right, so this is definitely a new kind of expression, and nevertheless it kind of smacks of a Riemann sum. There's a limit of a sum at the beginning. There's something which very naturally to the application I am kind of multiplying. It's dot product, but it's kind of multiplying. Times something which is kind of like length. It's just a little bit more than length. It's length and direction. So again, very reminiscent of integrals that we've talked about, just different. So we're going to call this a different kind of an integral. We're going to make this the definition of what we're going to call a vector line integral. And the notation is very natural. Very natural in the sense that the vector field that you evaluate on a given little piece of curve, you put there naturally. We use dx vector to represent the displacement delta x vector. Again, very familiar choice of notation there. And indicative of the fact that we're doing a dot product of those two things, we put a dot right there. So it's really extremely natural shorthand. Right? We're adding this up over our curve C. So that's our domain for this new kind of integral. So very natural notation. We have to give it a new name, though. We have to write this down as a definition because it really is technically a new kind of an integral. All right, is everybody happy? Anyway, that's the deal. In the previous example, we were computing the amount of work that it takes to blah blah blah. Notice in the calculation we did back here, the vector field that we were dotting with the displacement, etc. That vector field, you see right there, has a minus sign in it, so it's negative f. That is our integrand in this Riemann sum, and so that work is computed by a line integral of negative f dot dx. Okay. Now again, this is just Riemann sum talk. We're making definitions. Have not yet talked about how to compute these things. We'll get to that momentarily. But nevertheless, this vector line integral notation represents a Riemann sum, which would allow us to compute that work. Okay. So, yeah. Now, how do we compute these things? good news. We already pretty much have all the tools that we need to compute this thing. It's counterintuitive. This looks like a more sophisticated, it arguably kind of is a more sophisticated object than what we've talked about before, because it involves a dot product for one thing, vector differentials instead of scalar differentials. It is a new idea, and yet weirdly we've already computed all of these things. So in particular this dx object, we already talked about dx a long time ago. Dx is, well, it's this is a here, let me go back to this picture. Here you go. Dx is a vector representing displacement along one little piece of that curve. Dx, said differently, is the vector whose length we computed to find ds. ds being an object that we've already done stuff with, right? So dx we encountered along the way of computing something 3 sections ago. Okay. So here we go. There it is. There's our formula for dx. It's v dt. You can say this in sort of old familiar physics terms: displacement equals velocity times time. Okay. Now, 3 sections back when we were talking about scalar line integrals, we then said, well, yeah, but we really need ds. We need the magnitude of dx. We took the magnitude of both sides, and that's how we ended up with magnitude of velocity as our stretching factor. Here, we have no need for that here. Dx is the thing we need in the first place. So this computation here, trying to compute that vector line integral, this dx is v dt. Right, so put that right there, and the line integral becomes that, which I could rewrite like that. So handy dandy little formula there for how to compute these vector line integrals. And I've got that written down here somewhere. Yeah, here we go. As a theorem. If you want to compute a vector line integral, parameterize the curve, compute like so. That's how you compute it. Let me pause on this for a second. Does anyone have any questions about that? So, by the way, I think now would be a good time, or after class sometime soon, to go back to 3 sections back to the section on scalar line integrals and remind yourself specifically of where was it that we, in fact, did write down this dx, and in passing, we were on our way to this other thing, but just go back and confirm for yourself that, yeah, sure enough, we have already written that down. Yeah?
So why is the volume no longer needed?
What? Couldn't hear you.
Oh, so why is the force on that equation?
Oh, this is not necessarily to be interpreted as a force. This is just a vector field, general vector field. So here, what I'm doing here is I'm defining in the abstract this notion of a vector line integral. In that specific application we were looking at of work, then yeah, you need to have a minus sign there. Yeah, right. See an example. Okay, so let's compute the amount of work that it takes to walk along a certain path. The path is counterclockwise on the unit circle from that point to that point. So we're going to be starting at 1, 0. That's kind of the right-hand side of the unit circle. We're going to go counterclockwise, so therefore sort of along the top of the circle, to the point -1, 0. And I'll bet I have a picture of that somewhere. Yeah, here we go. So we're going to start here and end there, going like that direction. Okay. So now, right, fine. So that's the path we're going to walk along. Now the wind is blowing, and be very careful of the phrasing here. The wind necessitates pushing with an opposing force, and the opposing force is given. Now, do I need to multiply by -1 here? Actually, no. Carefully looking at the phrasing in this question, I'm not telling you the force the wind is applying to me. I'm telling you the wind that I have to push back with. I'm giving you the opposing force that I am applying. There it is, right? So in some sense, I'm the minus sign is already in there, as it were. Does that make sense? So this is a perennial, trivial annoyance that you're going to have to worry about when you're computing, certainly work integrals, but vector line integrals in general. You have to think carefully about, wait a second, do I need to put the minus sign in there or not? It comes down to looking at the phrasing, specifically what is it that is given to you, and you have to interpret from that and make the right choice as to do I need to put a minus sign in there or not. Is everybody on board with the choice that I've made here, given the way the question was phrased? Any questions about that? All right. So we've got a path. We've got a force. We already know that work is computed as an integral of a vector line integral of the force. Specifically, this force is the force that I am applying. So no additional minus sign required. And so here we go. And now we're just going to compute this vector line integral. Don't forget, we have a handy-dandy formula for computing vector line integrals. Parameterize the curve, and then plug in. Okay. So we're going to parameterize this curve here. Hang on. The curve, counterclockwise on the unit circle, from that point to that point, parameterized like that. Now again, that's an old chapter 2 exercise. Remind yourself of how to parameterize the unit circle, think about which way you're going. We've arranged for this to be an easy parameterization so we can focus on the vector line integral part of the problem. But make sure you're good at parameterizing curves, again, back in chapter 2. Yes?
So what if neither is negative?
What if what?
What if neither x or y is negative? Which one do we have to make negative?
Well, so now this force is given.
Yeah.
So I guess I don't understand your question.
So when the force is positive, we don't have to make it negative?
It's not about whether the specific coordinates of the vector field are positive or negative. It's about whether what you're given is the force that you are applying or the force that is being applied to you, which you then have to oppose with a minus sign. Right? So the question is not about this minus sign here. The question is about what's the phrasing here that so necessitates pushing with an opposing force. So that's telling me that I have to push with, and then it's giving me exactly the force that I'm pushing with. Does that make sense? Yeah. So the fact that there's a minus sign in that formula isn't it's not our problem, as it were. Yeah. Okay, so we have a parameterization of the curve, and note that the formula tells us I need to compute the velocity. The velocity is what's going to help me eventually compute my dx vector. The way I compute velocity is by taking the derivative of that parametric curve. Again, old chapter 2 fact. And now it's plug and chug. So let's see here. So dx is v dt. There's the velocity that I computed. That velocity is that. Notice that my parameterization, x of t, I just plug that in right there. So x is cosine t, y is sine t. Just plug that straight in. The vector field that I evaluate at cosine t, sine t is here. So it's negative y comma x. So again, now this is just plugging in. Here, let me. Got a lot of colors going on here, but that's fine. So negative y comma x. Plugging straight into the formula for the vector field. So I haven't really. All I'm doing is plugging into that formula above. And punchline is I have an integral. That's now a single variable integral to compute. It simplifies very nicely. In this case, I did that on purpose. Right? And so this is an easy integral to calculate. The answer is pi. All right. So I'm going to let you guys look at the other examples in this section. They're structurally really just like this one. It's just a matter of identifying that what you're computing is a vector line integral, parameterizing the curve. They're just slightly different curves, slightly different force fields, and plug into this formula. One last observation I do want to make about, before I go into the next subsection, about the computation of vector line integrals. Again, we already talked about how it's a little counterintuitive that even though this is arguably a more kind of sophisticated object, it's got vectors and dot products involved instead of just the good old-fashioned scalars. Not only is it surprising that, in fact, we've already done the analysis of how to compute this thing. I mean, all the objects in question in this vector line integral we already know how to do from previous discussions. But furthermore, the computation itself is actually easier than with scalar line integrals. And the reason why is, specifically, with scalar line integrals, the velocity, I had to compute the magnitude of the velocity. You notice in this case, no magnitudes. I'm not interested in the speed, thus helping me compute length of the little piece of curve. So no square roots to compute. Square roots are, at best, minor inconvenience. At worst, they can make an integral very difficult or even intractable. No square roots in this? Much nicer. Okay, yes?
When we parameterize, why is the domain conserved?
Yeah, so that's just, if you think about so let me draw a picture of the path. Our path is, so we started at, I already have a picture of the path. Here it is. We started at 1, 0, right? And we end at -1, 0. And I parameterized, I already have a point here, don't I? We parameterized by using that angle as t. So if you just think about, well, what is the value of this angle at our starting point? That's t equals 0, right? And I go along, and at my ending point, the value of that angle is pi. Does that make sense? All right. Okay, so lots of good news with these vector line integrals. Again, new object computed with familiar objects, and furthermore, no square roots to worry about. So it's really very, very good news. Okay. Other examples, again, I'm going to let you all read these examples on your own. They're very, very similar. So I want to move on and talk about how this relates to the unit tangent vector. You might recall we talked about the unit tangent vector back in chapter 4, I guess it was, when we were talking about derivatives of parametric curves. And so it's just the vector that's pointing in the direction of motion. So it's, said differently, the velocity vector divided by the magnitude of the velocity vector. It's the unit vector pointing in the direction of the velocity. Okay. So let's think about how our dx vector relates to that. Well, I think it's a pretty easy sell that the dx vector is the length of that little piece of curve times that unit tangent vector. And let's sort of think through, why is that? Well, an old fact that we already know is that dx is a vector that, to a very large degree, sort of represents that piece of curve, so it points in the direction of that piece of curve. Its magnitude is the length of that little piece of curve. That's exactly what this product is. Unit vector t means it's pointing in the direction of that piece of curve. T being a unit vector, the other factor is the magnitude, so the magnitude is the length of that piece of curve. This, you can see right in this product how this product, TDS, has all of the features that dx we already know has. So dx is TDS. Now, previously, we thought of dx as VDT, which it is, and that's nice. Right? But here's an alternative point of view on dx, TDS. Okay, so suppose that I used that to plug into my vector line. I've got this vector line integral here, integral f dot dxi, and suppose I forget about the whole parameterization and velocity business, and let's just rewrite dx equals ds. And what does that do for us? Does that bias anything? Well, it gives us a different interpretation of what this might represent. Specifically, note that you can do your parentheses like that, and it allows you to reinterpret a vector line integral as something which kind of looks like a scalar line integral. And that's a neat connection. I'm going to zoom in on that for emphasis. We have an integral ds. Right? So there is an object in here which I'm multiplying by the size of the little piece of curve and adding up over the curve. So now, still, I think it's worthwhile to observe that this vector line integral is a different kind of integral. This really is a new kind of an integral. But it is closely connected to this old scalar line integral construction. And it's tempting to say, oh my gosh, look, it really is a scalar line integral. You can see right there, look, integral something ds. The one twist that makes this not really quite technically a scalar line integral, it depends on how you want to look at it, but the thing that's definitely different is if you look at this integrand, that integrand doesn't just depend on x. This is not just a function of x. It looks like it is, but it isn't. There's a hidden dependence on the curve. And that is that this expression, this dot product, depends on the unit tangent vector, which depends on which direction is the curve pointing. And so you can't just give me an x and I'll just plug into a formula and know what this integrand is. I need to know what's the curve doing. So this integrand depends on the curve in a way that our old scalar line integrals never did. Okay. Right. There's another valuable punchline from this, and that is to remember that. Dot product with a unit vector gives you a component. There's an old chapter 1 reference. So this integrand, yeah, you can think of it as f dot t. You can also think of this as the component of f in the t direction. Said differently. Now, I'm going to take a different physical interpretation, and this is a big twist here. Previously, we've been thinking about this vector field. Our only application, our only sort of picture that we've had in our mind of what this vector field represents was forces. That's how we motivated this construction in the first place. But now, let's take a totally different point of view. Let's pretend that this vector field represents a fluid flow. What would this mean if I interpreted F as a fluid flow? Well, I've got this fluid flow, F, and this says I want to know to what extent is the fluid flowing along the curve. Right? So the T component, T is pointing in the direction of the curve. So this says to what extent is the fluid flowing along the curve. So that gives us a different point of view, a different way to think about vector line integrals. This point of view says the vector line integrals, in some sense, says, look, we want to keep track of the extent to which the vector field fluid is flowing along the curve, and we want to add that up over the entire curve. So a nice application of that, well, there's lots of applications of this. I'm going to give you one that you might be familiar with. Maybe this is your house, and here's your room. Oh, how about this? Let me put a door on that room. Right, so there's your room, there's a door. And then there's going to be, an air vent, let's say right there, for the air conditioning to let air in. And then, it goes up into the attic, and there's a, tube, etc. It goes into the air conditioning unit. Okay. And then there's an intake in a different room. Let me draw a different room over here. Whoops. Maybe there's a room over there. And wherever this air, who knows where this air intake is? Maybe it goes. Okay. So, how does air flow with your air conditioning system? It doesn't just blow cold, right? It blows cold air. So there's an actual flow of a fluid that's involved when you're using an air conditioning unit. And the fluid flows, well, if it's going to come out into your room, it has to have come from the air conditioning unit, which means it has to have come into that air intake. Where did that air come from? Well, it's got to have come from where the air is being put out into. Right? It's not spontaneously generating air to blow in. There's a conservation of air in this system, right? So altogether, then, there is a flow of the fluid of air through the air conditioning system. Now, your parents might have observed to you that, again, if your system's set up like this, that you have to keep your door open if you want to get air circulation. Do y'all remember? I don't know. My parents used to hassle me about that, right? Okay. So, perfectly natural term, talk about the air circulating because the air is going around in kind of a loop, right? Well, we now actually have an object. We have this vector line integral that's representing something kind of like what we're talking about. Namely, we just got through talking about how this represents, in some sense, the extent to which the fluid, vector field F, is flowing along the curve. Well, air circulation in this context might be thought of as the extent to which the vector field representing the fluid flow is flowing along this curve, this path that makes a loop that goes through your room and the air conditioning system, right? So this vector line integral is a way of representing what your parents always called circulation. So guess what the term is that we use to represent this interpretation, this point of view on a vector line integral around a closed curve. We call it circulation. Right? So your parents were making references to multivariable calculus whether they knew it or not. Right? And I think it's kind of a fun little observation. Now, specifically, we only call this circulation if, in fact, it's a closed curve. It's got to be a closed curve. If it's not a closed curve, the term doesn't apply. Okay. We're actually going to talk about circulation a lot when we get into Chapter 6. So, pretty soon, actually. Tomorrow, in fact. Okay. Right. So now let's talk about other potential merits of this little alternative point of view on vector line integrals. Will this help us compute vector line integrals? And I'm going to say usually not. So specifically, if I were to take a vector line integral and say, hey, let's compute that by using this formula, how would I compute that? Well, ds is v dt. Magnitude of v dt, that is. So notice, effectively, you are then just computing the velocity vector. You're just computing the velocity vector. Same velocity vector you would have had to do to compute it the other way. You're just computing it sort of in different chunks. Right? In practice, in fact, you would probably do this. You would probably be writing down, you would compute that unit tangent vector t as v over the magnitude of v. You can be computing ds as magnitude of v dt. So why compute the magnitude of v, multiply and divide by it if those factors are just going to cancel? You might as well just compute integral f dot v dt in the first place. In other words, most of the time, if you're going to do a plug and chug directly from a parameterization computation, that old formula is really better. And this is make work. Everybody see why it accomplishes nothing to do it the other way? Right. Okay. So let's very quick summary here of vector line integrals. This is the natural notation for it. It's my favorite notation for it. I like the fact that in this notation you can see exactly the vector field that you're studying for whatever reason. Fluid flow, force, whatever. And this dx vector very naturally represents the little piece of curve to which you're doing this dot product and then adding up over the entire curve. Specifically, dx, it points in the direction that the curve is going. Its magnitude is the length of that little piece of curve. In some sense, dx tells you everything you could ever want to know about that little piece of curve. So, very simple and natural notation. Computationally, that one's very handy. If you have a parameterized curve, or if you can parameterize your curve, that's a plug and chug formula. Very nice. This formula, nice for an alternative interpretation. Allows us to think of vector line integrals as relating to fluid flows instead of forces and works. So, and side note, this is going to be very important when we're, again, I cannot emphasize enough, when we get into chapter 6, one of the big objects of study we're going to talk about is circulation. So, making sense out of how circulation relates to vector line integrals comes by way of that alternative form. Okay. All three of these forms come from the fact that that vector differential dx can be thought of in these three different ways that we've already talked about. So, okay. So next section, vector surface integrals. Now, we talked about scalar line integrals, and then immediately followed that up with scalar surface integrals. Both scalar integrals, but one's over curves, one's over surfaces, but they had a lot in common, right? Same kinds of questions might come up. They're just dimensionally different. You can compute the mass of a one-dimensional rod in space, or you can compute the mass of a two-dimensional surface in space. Analogous, right? Just different dimensions. So you would sort of expect, having just talked about vector line integrals, that vector surface integrals might be pretty similar, and they are very similar in their algebraic construction. That what's different is in how we think about them. There's a different physical application that motivates writing down vector surface integrals. It's something called flux. I'm curious, I think I know, but I'm going to ask anyway, show of hands, how many people know what flux is? Very few. Okay, so fair enough. So let me give you a brief intro to what flux is. It's kind of a physics concept, but it's very physically natural. And this is going to be the physics question, the answer to which will motivate our new kind of integral. Okay. All right. So here it is. It's the rate of fluid flowing through a surface. It's called flux. So specifically, if you have a surface here, imagine my hand being a surface, and let's suppose there's some fluid flowing around in space. I want to know to what extent, not to what extent is fluid sideswiping the surface. We don't care about that. I want to know to what extent, how many cubic inches per second of air is flowing through. Let's imagine my hand is permeable. Right? Let's imagine my hand represents a net. Right? So to what extent is air flowing through the net? Don't care about along the net, just through. Okay. A possibly a little more natural metaphor for this. Imagine net fishing. right? You know, they take these big boats and they go out into the water and they drag these big nets behind the boat. Well, those nets are surfaces, and water is flowing through the net. So how much water is flowing through the net matters, right? If they just let the net sit there, if there's no water passing through, you're not going to catch a lot of fish that way, right? Alternatively, if you were to just grab the net by two ends and drag it behind you, well, now the surface is going to be like this, and the fluid would be flowing along the surface. Again, you're not going to catch fish, right? Fluid, the fish would just kind of swim right along and say, hey, look at that, there's a net, and keep swimming, right? So what you're interested in is the extent to which water is flowing through the net, because a given unit of volume of water, you're going to expect to have so many fish, and that's the fish that are going to get caught in the net. Okay. So physically, pretty natural thing, right? How much volume of water is flowing through. Oh, that's a bad. Let me try that again. Right, how much volume of fluid is going through your surface? Does that make sense? Okay. We'll talk about how to compute that now. I'm going to start with a simple version of this. Namely, we're going to talk about what happens if you have a constant vector field and a flat surface. We'll start with the easy version, and we'll work our way up to what happens if you have a curved surface, what happens if you have a non-constant vector field. But the easy first problem is a good starting point. We have to clarify one thing, and that is which way do we want to keep track of fluid flowing through the surface. If you have a surface, fluid flowing that way is pretty different, really, than fluid flowing the other way. You want to know there's going to be some direction. That's the direction that you want to call the positive direction through the surface. This is kind of like with line integrals. Go back one section. Let's think about line integrals representing work. Suppose I give you a curve and a force field, and I say how much work to move along the curve. Well, it depends. Are you going from here to here, or are you going backwards from here to here? If you're driving along a road, and let's say the road is uphill, and how much work does it take to drive this road? Well, going up the road takes a positive amount of work. Going down the road takes a negative amount of work. So very different depending on the direction. So very similarly, we need to define a positive direction through the surface. It's an arbitrary choice. We're going to indicate it by this unit normal vector. Make a better picture there. That unit normal vector there, we're going to call it little n. And its job is to just indicate what we are designating as the right direction, the positive direction through the surface. And that'll either be given to you in the question that you're answering, or naturally interpretable from the application that you're trying to resolve, or whatever. Okay. Right, so that being said, how are we going to actually, terminology, we call that an orientation on the surface. So how are we going to actually compute this? First observation I want to make is that the vector field can be thought of as having two different components. It's got a perpendicular component and a parallel component. Looking at this picture here, this vector field vector there, to some extent, that is pointing perpendicular to the surface, and then to a different extent, it's pointing parallel to the surface. So this is what I'm going to call F parallel, and this is what I'm going to call F perpendicular. Right, any vector field, any vector in relation to a surface is going to have a part, to some extent it's going to point perpendicular, to some extent parallel to that surface. So we are interested in that part, right? The extent to which the fluid is flowing through the surface. I don't really care about the extent to which the vector field is flowing along the surface. You don't go through if you're going parallel, right? So we're going to throw away that parallel component. Don't care about that. And I'm just going to argue that, well, if I know how fast, that's the speed of the fluid through the surface, and if I multiply by the area of the surface, that's going to tell me how much fluid is flowing through the surface. Seem like a reasonable definition? More speed, the faster that it's moving, the more gallons per minute are going through your surface. The bigger the area, right? The bigger your net, the more fish you catch. The faster you drag it, the more fish you catch. Yeah.
Does this account for things that are, like, I guess, like if water is not going completely parallel to this, perpendicular to the surface?
Yeah, it does. Because so the extent to which it's not moving, so look at this picture here. The vector field is this green vector, and it's not moving perpendicular to the surface, right? But that green vector I can think of as having two components. And it's always got two components, and I never care about the red one. It's just, that's the irrelevant part. It's the part that's perpendicular, the part that represents the, how much is moving through that I care about. Yeah. Right. Okay, so this is our sort of starting formula, and then remembering that a component is computed as a dot product. I can rewrite that like that. And so our formula for flux becomes this, and that's the one we're actually going to work with, F dot N times area. Right. Now then, so this formula is, again, sort of our starting first shot at understanding flux, but in particular, this requires the vector field to be constant. We're assuming it's constant. It says we're looking at a flat piece of area. Okay, so a lot of assumptions that went into this formula, but this is going to be enough to get our foot in the door. Okay, there's an example here. You guys can read this. It's quick and cute example. It's non-critical, but give that a look if you're curious. So now let's consider the harder question. Suppose you have a non-constant vector field. It's going to change things. Suppose you have a non-flat surface. Well, now, which direction is the normal vector? How do these components break down? It's different in different places. It's a harder problem. But flux accumulates over the surface. Said differently, you have a great big net, curved though it may be, the grand total number of fish that you catch is the sum of the numbers of fish that you caught in each segment of the net. Okay? So it's an accumulating quantity, kind of like mass, kind of like all the other accumulating quantities we've talked about. Each of those little pieces is small. Over a small piece, the vector field is roughly constant. So all of that makes sense in the context of our old formula. So on each little piece, the constant and flat formula on the previous page will allow us to write down the amount of flux that happened through each piece. So in particular, I'll just go back to here. F dot N times area on a piece of surface. F dot N, the area is delta S. That's the good old delta S from scalar surface integrals we talked about last time, just the area of that little piece of surface. So here I'm plugging straight into the old formula on the previous page and getting a new kind of a Riemann sum that represents this flux quantity. So again, looking at this expression, we have to acknowledge that's not really exactly it's kind of a scalar surface integral, sort of. We're adding up over a surface. We're multiplying something times area. But you notice that it depends on the orientation of the surface. It's not really a scalar quantity exactly. Right? Something is definitely different because it depends on how the surface is oriented. So we're going to call this a new kind of Riemann sum, and we're going to give it new notation. Very natural choice of notation. Again, delta S, we're writing as ds, f dot n. The summation is the two integral signs. So very natural choice. Okay. So this is just a definition. And now what does this compute for us? Well, we've got the one application so far. This computes flux. Okay. How much of a fluid is flowing through a surface? We're going to find that this is actually interesting in different ways when we get into Chapter 6. But the best physical metaphor, the best way to think about this, what I'm calling a vector surface integral, is to think of it as fluid flux. All right. Now, a notational twist. That object, f dot n ds. I'm going to rewrite that a little bit. We had sort of thought of it as, let me zoom in a notch. We had thought of it as f dot n times ds. Let me just point out I could write that as f dot n ds. It's the same thing. I'm just kind of moving the parentheses around there. But what's nice about this point of view is that I can now think of NDS as a single thing. And NDS is a natural pairing of factors. Let's think about what NDS represents. N is a unit vector representing the way our little piece of surface is oriented. If our piece of surface is oriented like that, N, that little unit vector N, is indicating by being perpendicular to it how that little piece of surface is oriented. So we've got a vector here whose direction tells me about the orientation on the surface. And the magnitude of this vector is the area of that little piece of surface. The magnitude is ds. So in the same way that dx, let me write this down, in the same way that we thought of dx as being t d little s, and we thought of this as being orientation of the piece of curve times the size of the piece of curve, and therefore this tells you everything you could possibly want to know about that piece of curve. Likewise, here, orientation of the piece of surface, size of the piece of surface, and therefore this thing, what I'm calling the ds vector, tells you everything you could want to know about that little piece of surface. So this is a vector surface integral analog of the dx vector from vector line integrals. Okay. Great. Okay. So I also just like the way this notation looks. It's very sort of compact. There's the integrand telling you about what you're doing an integral of. There is the vector differential telling you about the little piece of surface. Very compact, natural notation. Okay. All right. So let's talk about how to compute these things. Again, good news. Turns out we already pretty much have everything that we need. Let me remind you what we've already done on surfaces when we parameterized surfaces for scalar surface integrals. And we were studying a little piece of surface. We found ourselves interested in these two edge vectors, xu du, xv dv, because they're the edge vectors of this little parallelogram. Is where you're going to take the cross product, compute the area of this thing, all the formulas we worked out a few sections back. The punchline was that this vector, capital N, was convenient for writing that down. We ended up needing to write down xu cross xv, and that's what we called capital N. Don't forget that we have already talked about, let's see, color choice. Here we go. The unit normal vector. So that's, being as it is the unit vector pointing in the capital N direction, it's capital N divided by magnitude of capital N. And we just got through defining this this ds vector, that vector sort of being the all-encompassing everything you could want to know about that piece of surface, namely its magnitude is that area and its direction is telling you about how the surface is oriented. So that's what we know. These are the objects that we've developed, some a few sections back, some moments ago. And let's notice then that I've got everything that I need to compute. So specifically, if I'm interested in computing this, highlight. I'm interested in computing that. I'm interested in computing a flux, a vector surface integral. What I really need is to know how to compute that ds vector, which we just defined as being in ds. So how do I rewrite this ds vector now in terms of the parameterization? Well, don't forget, old fact, ds is length of n du dv. And now, in this expression, let me just move the parentheses around. So instead of grouping those like that, let me just group those two together. Didn't really do anything. Just move the parentheses. And conveniently now, this is exactly the capital N vector. Think about it. This little n points in the direction of the capital N vector. This product, because little n is a unit vector, has magnitude that is the magnitude of the capital N vector. This product, it points in the same direction and has the same magnitude as capital N. So it is capital N. So there, then, is our handy-dandy formula for how to compute the ds vector. The ds vector, in terms of the parameterization, is capital N du dv. And we already know what capital N is. Capital N is the same capital N from 3 sections back. It's xu cross xv. So plug and chug at this point. So we'll see an example. There's one little twist that we need to worry about, but basically most of what we're going to need is right there. Everything here is in terms of the parameterization. Okay, so let's see an example. The surface in this example is a familiar old surface. Right? We do this a lot. Specifically, it's the part that's above the unit disk in the xy plane. I just want to talk about just that one part of this paraboloid. Notice that I've given you an orientation. It's oriented downward. Let me draw a little picture relating to that. Oh, yeah, here we go. Here's our paraboloid. This is a surface, and there are two different directions that one might be interested in fluid flowing through that surface. So the two different choices are that and this. Right? So you could, how we describe these, we're going to have to do some hand waving because the surface is curved. None of these, this blue vector points in a different direction depending on where you are on the surface. So I guess you could call the red vector is kind of pointing inward and the blue vector is kind of pointing outward. You'll also notice that everywhere on this surface, that red vector is going to be pointing at least to some extent upward. The blue vector, everywhere on this surface, pointing to some extent downward. Right? So when you find yourself talking about orientations and which orientation do we want to pick, the idea is to try to find some uniformly shared characteristic of the vectors that you're interested in. In this case, these blue vectors, this is the orientation I want to talk about, is the blue orientation. all those blue vectors, no matter where you are on the surface, they all point, to some extent, downward. So if I say, given this surface, oriented downward, it should be clear that this is the orientation I'm talking about. All right, so it's going to actually be downward there. It'll be somewhat downward there, somewhat downward, less so, but still somewhat downward over there, always somewhat downward. There's no way I'm talking about that orientation. That's never downward in any sense. It's always at least somewhat upward. So the terminology is not going to be precise when you're talking about orientations. It'll be, it'll allow you to be clear which orientation we're talking about, but it's going to be a little vague. Does that make sense? All right. So again, sloppily, slightly sloppily, we're going to call that a downward orientation. Okay. Right. So oriented downward. The vector field I want to compute the flux of. Whoops. I wanted to change colors. Vector field I'm computing the flux of is that, and let's compute the flux. Okay. Going to use this formula. Okay, so I'm going to rewrite everything in terms of the parameterization. Going to have to compute that capital N vector. N is xu cross xv. So I've got to take some partial derivative. Well, I have to parameterize first, excuse me. Here's the graph parameterization of that surface. Xu cross xv, certain partial derivatives. Do the cross product, and there is your normal vector. Everybody on board? There's a problem. I swept that under the rug deliberately. This is something you always have to watch out for. Just got to be careful with it. So here's what the problem is. I've told us the statement of the problem, again, is that we're oriented downward. That's the direction I want my surface to be oriented. Said differently, that's the direction that my unit normal vector needs to point. But I also need to compute my capital N vector, and I'd like to do it with this formula, hopefully. The problem is that the direction that capital N points is kind of suggestive of the direction little n points, because capital N and little n are supposed to be related. Right? So in this case, though, look at what we got. Look at our capital N vector. Look at its third component. That's positive. I have, by the parameterization that I chose, I have created a capital N vector with a positive third component, which is therefore pointing to some extent upward. There is no sense in the word in which this is pointing downward. So inadvertently, I parameterized this thing upside down. So I made that capital N vector. I wanted to end up with a unit normal vector pointing that way. I parameterized it upside down. How would we say that? So, annoying. The bad news is that that's intrinsic to my parameterization. The way I wrote down this parameterization, an arbitrary choice, of course. Lots of different parameterizations you could make. But given that parameterization, this is how that calculation works out. So it would seem that I need to take this parameterization and chuck it and parameterize all over again and hope, fingers crossed, that this time I don't parameterize it upside down again. And I suppose you could do that, but it turns out there's a much easier solution, and that is simply to realize that all I really need is that's what I really want. I can just throw a minus sign on the capital N that I just computed. It doesn't really matter where it came from. It's perfectly fine. So just toss a minus sign in here. That minus sign is an acknowledgement that we parameterized upside down, and then proceed. You can use the backwards normal vector that I already computed. Just put in this fixer minus sign, and you're fine. Everybody see the idea there? You got to be careful about this. This is a big deal. If you're not careful with your orientations, namely if you use a capital N that's backwards, and if you don't fix that, then you're going to get the wrong answer by a factor of a minus sign. But I mean, it's an important concept. It's conceptually important. It will consistently, every time, make you have the wrong answer. So it's a significant problem. On exams, this is something that's going to matter pretty significantly, right? So this is not a -1 kind of a deal. This is more significant than that. Said differently, this is not an arithmetic oops. This is not I multiplied minus times minus and got minus. Wow, that's silly me, right? This is a conceptual oops, right? So this is important in a grading of a question. Okay, that being said, everything else is plug and chug. There's that normal vector. We plug the parameterization into the vector field. Plug in like so. Dot it. Dot product turns into that. And lo and behold, you've got an integral to compute. You can write it in polar coordinates. Turns out really nice in polar coordinates, and there's your answer. Make sense? Okay. All right. There's a couple other examples here. Again, like with the vector line integrals, they're pretty similar to the one that I just did. This third one is a little different. I do want to talk about this one a little bit. Surface, sphere center at the origin, radius 3, oriented. So we've got a surface given to us. Got a vector field given to us, and let's compute the flux. There's flux. Okay, now you can parameterize that surface. It's no problem. It's a sphere. Use a spherical graph parameterization. Chapter 2, again, if you want to brush up on that. And you can plug and chug, and it will work out. It might be kind of tedious, but it will work out. I just wanted to show you a much more clever way to solve this problem, and that is to just take a different point of view on the flux, and that is to look explicitly at the vector field and the unit normal vector. Now, in this case, we can actually write down our unit normal vector because spheres have a lot of symmetries. If you think about it, if you have a sphere, right? Let me draw a picture. You have a sphere. Centered at the origin. Then at any point on the sphere, the unit normal vector is parallel to the position vector for that point. Said differently, you're just going to take the point, the vector representing the point, and the normal vector is pointing in exactly that same direction. So just divide that position vector by its own length. And that makes for a really easy formula here for the unit normal vector. So in this case, just happens to turn out that the dot product here, that dot product of these two things, happens to be 0. That it's not going to happen every time, right? But it's not the weirdest thing to ever happen. Sometimes you get geometrically lucky. It's a good thing to be sort of on the lookout for. The tip-off in this question was that it was a sphere, thus allowing me very conveniently to write down my unit normal vector. And having written down that unit normal vector, just glance up at the vector field and just notice that, okay, well, there's a yz that's going to multiply by then there's xz that's going to multiply by a y, and an xy that's going to multiply. There's a lot of xyz's in this dot product, and then that's a tip-off that, hey, this just might work out. Give it a look. Again, very often, nothing of the sort will happen, but sometimes. Okay. Okay, last thing I want to do is talk about the very strong analogy between vector line integrals and vector surface integrals. And I've got those analogies written down in these two pictures here, or a lot of them anyway. So in both cases, let me note what we have here. We have here a curve. You notice all of the usual objects of interest relating to this curve, parameterizing this curve, doing the line integrals on that curve. And over here we have a surface and all of its related objects of interest. Now, in each case, our computations were done by parameterizing. Now, forgive me, I'm drawing my parameterization sort of vertically instead of horizontally here, because otherwise it doesn't fit on the page very well. This is strictly an aesthetic awkwardness. So, anyway, vertical instead of horizontal. In both cases, we use the parameterization related to a much more desirable piece of the parameter space, dt for line integrals, dudv for surface integrals. To get our hands on what we're actually interested in, here it's the length of a piece of curve. Here it's the area of a piece of curve. Right. I'm trying to color code the analogs here. Okay. In the line integral case, there's a single vector called dx that tells me everything I need to know about that one little piece of curve. Over here, there's this single vector ds. That tells me everything I want to know about that one little piece of surface. In both cases, these are computed by way of the parameterization from certain vectors. It's v, it's the velocity. In the line integral case, it's in the surface integral case. Now I've color-coded those blue, and the reason I've color-coded, I know I've already used blue. I used blue with the parameterizations. And that's because these vectors come from the parameterizations. X prime. You take the x parameterization and you take a derivative. That's how you get the velocity vector. N is, well, it's x u cross x v. You take the parameterization and take certain derivatives, the u partial, the v partial, and then you have to cross and find. But nevertheless, this comes out of the parameterization. Very natural. And then in both cases, there is a unit tangent vector. Well, excuse me, let's say a unit vector pointing in the direction of the orientation of the curve on the left and surface on the right. So the objects that go into analyzing how to get your hands on a vector line integral, and likewise for a vector surface integral, lots of analogies. We're doing a lot of the same things with vector surface integrals that we were doing with vector line integrals. They're just sort of contextually different, of course, but very analogous. Look how this shows up in the stuff that we write down. Oh gosh, I'm never going to be able to get these colors straight. Let's see, red. The dx vector, the ds vector, these two vector differentials, each of which represents everything you want to know about the little piece of curve or surface, depending. One of these vectors that comes from the parameterization times size in the parameter space, which is also a unit vector telling you orientation, times the size of the piece of curve or surface. Lots of analogies there. So dx and ds play analogous roles. X prime and n play analogous roles, etc. Capital T, little n play analogous roles. All the equations for vector line integrals have corresponding analogs equations in vector surface integrals. You can even see it in how the different forms of these integrals. So in both cases, we have sort of the simple notation. In both cases, there is a notation that directly relates to the parameterization. In both cases, there's sort of a unit vector notation that has interpretations one way or the other, particularly relating to fluid flows. Again, this is how we related vector line integrals to fluid flows. This is how we related, in fact, how we motivated flux as discussion of fluid flows, etc. So the reason I like to show students this analogy is that to whatever extent you have some intuition for what various objects of interest are on the vector line integral side, maybe you feel like you have a reasonably good understanding. You understand what ds is. Yeah, sure. Well, then that is a tool that you can use to give yourself a better understanding of what this ds is. Right? If you're not entirely clear on what's the deal with the capital N vector, well, it's a analog of the velocity vector, vector line integrals. And you can think about what you understand over here on the line integral side to give yourself sort of maybe a foot in the door on having an intuition what's going on with the surface integral side. One last quick comment, and I see that we're out of time. One might wonder, what are the odds, right, that this level of analogy would exist? Why? How could it be that these seemingly very different things, that the calculations are so analogous? And it turns out there's a wonderful answer to this question, and that is that both of these objects, line integrals and flux integrals, happen to both be special cases of a more general construction that we're not going to talk about in Math 212. It's beyond what we can reasonably do in this course. But they're both special cases of what are called integrals of differential forms. So they end up looking kind of alike because, in fact, they really are fundamentally kind of the same thing. They're different examples of a single construction, just in different contexts. So the fact that they end up looking a lot alike is really ultimately no surprise then. Okay, and I'm going to be talking more about that connection later on as well. So, okay, this is a good stopping point. See y'all tomorrow.